Hello everyone. I want to discuss section 5.2 on calorimetry. So the learning objectives here explain the technique of calorimetry and then also calculate and interpret heat and related properties using typical calorimetry data. So we are going to build on what we did in section 5.1 by applying the heat equation to a situation where we have an experiment designed to measure some of this stuff. So calorimetry is a process of measuring the heat transferred in a substance, so going either into or out of the substance. And in order to figure that out, what we have to do is we have to calibrate it by comparing it to something that we know for sure how much heat was going into or out of that substance. So what we end up doing is we define a system as some substance that's undergoing a change, could be a chemical or physical change, and surroundings, and that would be everything else that's around that. And the surroundings is what we use as the way of calibrating that process. So the surroundings could be providing heat to the substance, or they could be absorbing heat from the substance. So when we do this, what we do is we use a device called a calorimeter, and it is a device that is helpful in measuring heat involved in these processes. So we'll look at some examples of some calorimeters and then look at how we would do the involved calculations. So here we're looking at a situation where we have some exothermic process, maybe it's a chemical reaction that's going on, and when that occurs, energy is going out of that process into the surroundings. So we would see an increase in the temperature of that surroundings. Now, if we know what that surroundings is made of, if we know the heat capacity of those surroundings, and we measure the temperature change, we can measure Q. We can measure the heat going into the surroundings. We could do a similar thing for an endothermic process. So here we have a process that is absorbing heat from its surroundings, and as that occurs, the temperature goes down. But again, as long as we know the heat capacity of those surroundings, we can then figure out what Q is, and thereby figure out what's going on with that process. So we have some well-insulated objects that we use for this process, and something inside of that can absorb a lot of heat. And it turns out that the one we can often use fairly accurately is made of a coffee cup. So that might seem a bit low-tech to you, but if you think about it, a coffee cup is doing exactly what we want it to. It's insulating, it's keeping the heat from transferring out of the coffee into the surroundings. And it does a fairly good job of it. So we can use that for our experiments this semester. Here's an example of a coffee cup calorimeter. The setup is very similar to what we'll be using in the lab. So we have two nested styrofoam coffee cups. We'll have a cover for that, and then we'll have water that we put inside, as well as a thermometer and something to kind of stir the water within that so that it's all at the same temperature. If we were being really kind of exact in terms of wanting the best results, we would figure out, well, how much heat is the actual coffee cup itself absorbing? But for the sake of what we're doing, we're going to assume that any heat being absorbed is by the water inside. And the water inside, we know what the heat capacity is, and if we know how much water we have, then we can easily do a calculation to figure out how much heat is transferred. So let's look at some additional examples. So here we have kind of a more technical example. Here we have a motorized stirrer, high precision thermometer, and then insulation, insulated cover, and everything goes inside of it. Now this this is a lot more expensive and more accurate, but it's also a little bit more time consuming in that you have to calibrate the whole thing, because this is not just a simple coffee cup. You have to calculate everything going on here. So it is a bit more involved. It would be more time consuming if we had one of those to use. So we're going to start with a simple example of just a physical transfer of energy from a hot object to a cool object, and then we'll look at how the same principle applies for a chemical reaction. And the basic idea here is the conservation of energy. Any change in energy adds up to zero. And by any change in energy, what I mean is the heat transfer to or from one substance and the heat transfer to or from another substance. For this example, it looks like we are defining M as a metal, a hot piece of metal, and W as a cool water. One of the things you'll see as we start doing calorimetry is you will always have two or more things because heat is being transferred, and you want to have a clear label of which is which. So in this case, we have M and W, so metal and water. So whatever heat is transferred into or out of the metal, plus whatever heat is transferred into or out of the water, adds up to zero. Now for that to be true, one of them is positive and one of them is negative. And we usually rearrange it to give it this form. And this is saying whatever heat is gained by M is lost by W. Okay, whatever is gained by M is lost by W. Well, what if it's the other way around? It will still work out. Okay, whatever is transferred from one goes into the other. And you have to be aware of the sign convention in terms of knowing that what positive and negative means. So positive is going in, negative is coming out. So think of endothermic and exothermic for that. Okay. So here we're showing kind of what we expect to have happen. We have a hot object. Energy is flowing out of that hot object into the surroundings. As that happens, the temperature increases. Eventually, everything is at the same temperature. And everything being at the same temperature is one of the important things to understand about this process. Okay, so let's go ahead and talk through this example. So this example is discussing kind of what we had just talked about here, but putting some actual numbers onto it. And I want to talk through this example because there's a few places where there's some things that maybe are not obvious why that is the way it is, and we want to understand that. So we have a 360 gram piece of rebar dropped into 425 milliliters of water at 25 degrees Celsius. The final temperature of the water was measured as 42.7 degrees Celsius. Calculate the initial temperature of the rebar. Assume the specific heat of steel is approximately the same as that for iron, and that all heat transfer occurs between the rebar and the water. And so it says there is no heat exchange with the surroundings. So basically what we're assuming there, again, is that whatever this container is does not absorb any of the heat. All of the heat goes into the water, and we know how much water we have, and we can look up heat capacity that we need for it. Okay, so let's talk through this. So we can start with saying Q of the rebar is equal to negative Q of the water. Um, so heat is transferred from one to the other. So heat given off here is the heat that is taken up over here. So then for each of these, basically each one of these is a heat equation. So we would then replace that, each of these, with a heat equation. So we have heat capacity, or I should say specific heat capacity times mass times delta T for the rebar is equal to negative specific heat capacity times mass times delta T for the water. Okay, so again, very important to be clear about what these are for, because we have multiple things here, and each one of them is for a different thing. We'll have multiple heat capacities, multiple masses, multiple temperatures. So when we kind of expand that out, we have the heat capacity of the rebar times the mass of the rebar is equal to the change for the rebar, so final minus initial for the rebar. And then we have this side heat capacity, specific heat capacity of the water. So negative specific heat capacity of the water times the mass of the water times the change in temperature of the water, so final of the water minus initial of the water. Okay, so this is often going to be the first step of any calorimetry question where you are comparing heat transferred from one to the other. Then we go through and put in the numbers, okay? So we have the heat capacity of the rebar. We would look that up. We were provided with the mass of the rebar. We were provided with the initial temperature of the rebar. I'm sorry, no, we weren't. That's what we're trying to find. This is the final temperature of the rebar. Now, how do we know that? This is one of the tricky things, so let's talk about that. The final temperature of the water was measured as 42.7 degrees Celsius. Now, remember, the final is the point at which they are both the same. Everything is equal at the final temperature. So if the water is 42.7, then the rebar is also 42.7. So we can basically put in 42.7 for final for the rebar, as well as final for the water. And then also for the water, we can look up the specific heat capacity of water. We have 425 grams of water. We're assuming here, so that the density is essentially 1 gram per milliliter, and we have 425 milliliters. I know in the density lab we looked at, using that table to figure out, okay, what is the density at this temperature? We're not going to get to that level of detail here, as you'll see when we get into this. The significant figures where that would matter aren't going to matter here, because we have other things limiting our result. And then we have, again, final temperature is the same for both. And then we have the initial temperature of the water. Okay, so we have a lot of numbers in here. And what we do is we just need to rearrange it and solve for the unknown. In this case, the unknown is the initial temperature of the metal. So we have all of this on one side. We can do all of that math. And then on the other side, we're looking for this. So we divide by these. We're showing that here. And then we subtract that from each side, and then the sign changes. So we get this. Okay, so there's a bit of algebra there. Make sure you can go through and figure out how to do that, and then you can solve for the answer. There's another one that's similar. So if this is kind of a lot and you want more practice, there's a similar question you can look at here as well. Another example where we're solving for something other for the specific heat to identify a metal. So you can look at another example. Again, it's going to start by using two heat equations. You're just solving for a different part of it. Okay, so that is one thing we can do with calorimetry. Another way we can look at this is when we have a chemical reaction. So here we would say the heat of the reaction plus the heat of the solution is equal to 0. So it's essentially the same idea here, but instead of two things changing temperature, you really have one thing, which is the solution changing temperature, and then we figure out, well, what is going on with the reaction if that happens. So some examples here of that, we will be doing some of this in the lab as well. You'll notice this one is not quite as involved because you're basically finding the Q of the solution. You're not having to do two heat equations, and then you'll be using that to do additional calculations, and we'll look at that in the lab. And then I did want to end with this other type of calorimetry. This is called a bomb calorimeter. And in a bomb calorimeter, we do it a little bit differently. We put a sample inside of a sealed container. So this container is sealed compared to the one we had for this example was open to the air. So air can get in and out of there. And air could get in and out of this one as well. Whereas this one is sealed. It's pressure sealed. You have a very high pressure inside of here. This is called the bomb, and then you have something in here that you are basically igniting. And then the bomb is placed into this larger container that contains usually water, and you measure the change in the water temperature. And from that, you can determine similar things. Now, one of the differences here is that this is a sealed container. The other one was not a sealed container. That's a really significant difference. And we'll see why when we get into later into this module, that there are more than one type of energy, and the way we measure that energy determines which type we are measuring. But that is it for this section. Please look at some calorimetry examples and do some of the worksheets, because again, this will continue to build as we move further into the module.